We are used to the magic of the grid. You flip a switch in your kitchen, and instantly, a power plant miles away feeds that demand. It is clean, it is convenient, and it happens entirely out of sight. But eventually, every power plant reaches the end of its life. For a nuclear facility, that closure looks like a clean break. The operators drop the control rods, the active fission chain reaction halts, and the plant officially stops generating electricity for the outside world. You cannot, however, just turn a reactor off and walk away. Inside the core, uranium pellets sit stacked inside long zirconium alloy tubes. Even though the active splitting of atoms is done, the resulting byproducts left inside those fuel rods are highly unstable. They continue to decay naturally, throwing off intense radiation and generating massive amounts of physical heat. This is decay heat. If you simply pulled those fuel rods out and set them on a factory floor, they would rapidly heat up, melt right through their steel casings, catch fire, and release a lethal cloud of radiation. The power plant might be dead to the outside world, but backstage, a massive, highly engineered logistical operation is just waking up. For the next several decades, engineers have to manage the most dangerous heavy cargo on Earth. The first stop for this spent fuel is inside the facility, in a heavily reinforced 40-foot-deep thermal management trench known as the spent fuel pool. The thick layer of water in this pool serves two critical purposes. First, it acts as a physical radiation shield. With roughly 20 feet of dense water sitting over the assemblies, the radiation is entirely blocked, allowing technicians to safely walk on steel grating right over the glowing rods. Second, the water is a coolant. It constantly strips away that intense decay heat, keeping the fuel assemblies from overheating. But because the fuel never stops generating heat, the pool needs an active mechanical system to keep it from boiling. This requires massive industrial pumps continuously cycling the water, a steady supply of electricity from the outside grid, and backup diesel generators waiting on standby in case that grid fails. This wet storage system requires flawless, uninterrupted maintenance 24 hours a day, but it is only a temporary necessity. After 5 to 10 years, the fuel's thermal output naturally drops enough that plant operators can prepare the waste for its next stage. The ultimate goal is to transition the waste out from this active, high-maintenance wet pool into a dry, passive environment. This begins entirely underwater, where robotic handling tools carefully slot the fuel assemblies into a precision-engineered heavy-duty steel canister. Once the grid inside is full, a thick steel lid is lowered into place. Still fully submerged, robotic arms weld the canister completely shut, utilizing the dense pool water to shield the technicians from the radiation. A heavy lift crane then hoists the heavy payload out of the pool. Now a new physical problem arises. The inside of that newly welded canister is full of water. If you leave liquid trapped in a sealed, heat-generating steel drum, it will boil into steam, build immense pressure, and rupture the walls. The oxygen in the water would also cause the metal rods to rust. To solve this, crews attach heavy-duty industrial vacuums to a small port on the lid. They pump out every single drop of liquid and then pull a hard vacuum to suck out any remaining moisture until the interior is bone dry. Finally, they inject the canister with pure helium gas and weld the final port shut. Helium is an inert gas, which prevents the metallic fuel rods from chemically corroding. Even more importantly, it is a highly efficient thermal conductor, pulling the decay heat from the rods straight to the outer steel wall of the canister. Through this unbroken chain of physical isolation, the dangerous material is permanently moved out of its volatile, water-dependent state. The sealed steel canister is then lowered into its final physical shield, an overpack made of heavily reinforced concrete and structural steel. Fully loaded, this 100-ton monolith is called a dry cask. If you just trapped all that decay heat inside solid concrete, the internal temperature would spike, cracking the structure and causing the system to fail. So the engineers rely on convective thermodynamics. In this cross-section of a dry cask, there is a narrow gap between the inner steel canister and the thick outer concrete shield. As decay heat warms the steel, it heats the air inside that gap. Basic physics dictates that hot air rises. It travels up the gap, escapes through exhaust vents built into the top lid, and creates a natural vacuum that pulls fresh, cold air in through vents at the bottom. The cask continuously cools itself using nothing but natural airflow. It requires no pumps, no human intervention, and no electricity. Once these monoliths are securely placed on concrete storage pads outside, the rest of the massive power plant can be completely torn down, imploded, and returned to nature. The system achieves total thermodynamic equilibrium. The lethal cargo is secured using nothing but gravity and the predictable behavior of moving air. Right now, thousands of these concrete monoliths sit quietly on storage pads across the globe. They are safe, but they are stranded. Eventually, they have to be moved to a permanent deep geological repository where they can safely decay for the next 10,000 years. Moving them is a logistical nightmare. You cannot simply put one on the back of an 18-wheeler. The sheer point weight of the steel and concrete would instantly crush the truck's suspension and destroy the asphalt highway underneath it. Instead, moving this material requires a separate heavy-haul infrastructure network. It starts with specialized crawler transporters, similar to the tracked machines that carry rockets to launch pads. These vehicles use dozens of wheels to distribute the massive load so the concrete does not shatter, carefully extracting the inner canister into a custom transportation cask. These transportation casks are built strictly for chaos prevention. Before a design is approved, engineers subject it to extreme physical stress testing. They crash locomotives into them at 80 miles per hour. They drop them onto steel spikes from 30 feet in the air, and they burn them in jet fuel at 1,500 degrees Fahrenheit, all to prove the physical integrity of the canister cannot be breached. Once the payload passes these extremes, it is bolted onto a custom-built heavy-duty railcar. While a normal freight train car uses 4 axles, these can have up to 12, specifically engineered to spread out the extreme weight of the shielding so it does not warp the steel train tracks as it moves. Then the journey begins. These trains move at heavily restricted speeds, escorted by armed security and tracked by satellite. They navigate a highly specific physical network of cleared rail lines and structurally reinforced bridges, ensuring the cargo never encounters a physical shock it cannot absorb. We expect our modern utilities to be invisible. We want the benefit of a fully powered grid without the burden of its creation. But the physical world demands a toll. Long after the power plants themselves fade into history, a massive, silent logistical machine remains at work, ensuring that we never have to notice the legacy left behind.